All right. Good afternoon, ladies and gentlemen. My name is Ben Holmquist, and I'm joined by my friend and colleague, Daniel Enriquez. We're here today to represent the Eclipse rocketry team from the University of California at Davis. Now, this team is 20 members strong, with individuals from all over the academic map. Dan and I are happy to stand up here and take credit for all their work for last year. Now, this work has been spurred by an Inspiration Mars design competition started by Dennis Tito in Inspiration Mars. Now, they requested a 2018 Mars flyby, and this is only 4 years away, so it's a very abbreviated time schedule. Now, Daniel's going to give you an overview of our mission design for last year and how we think this mission can actually be possible.
Now, as Ben said, we worked hard over the last year to come up with this concept of operation. Our mission profile dictates 3 separate launches with an assembly of our spacecraft in low Earth orbit. On January 5th, 2018, the final assembly will burn into a trans-Mars injection burn, and over the course of the mission, a closed-loop life support system, a combination of both passive and active radiation shielding technologies, and a whole slew of medical diagnostic equipment will maintain and monitor the crew's health. This is to ensure that they're safe for the last leg of the journey, the re-entry. For the re-entry, we will fire an RS-72 booster to slow the capsule down to a manageable level, and they will then perform a skip re-entry, which will bring them into Earth's atmosphere. We will deploy parachutes, land safely into one of Earth's oceans, and into a warm welcome by every major news network on Earth.
Now, Daniel just did a good job in 1 minute of packing a huge mountain and diverse array of technical challenge that's required for this mission. In tackling this almost a year ago, we decided the logical place to start was with our launch systems and what spacecraft could actually take 2 humans to Mars and back. Now, we selected the SpaceX Falcon family of launch vehicles for our 3 launches, and the Falcon Heavy really is the keystone, we think, to making this mission possible. Mainly because of its lifting capabilities of 53,000 kilograms, which really dwarfs the competition that's going to be available by 2018. It's also a great value at $77 million a launch. So our first launch is coming from Cape Canaveral Air Force Base in Florida. This launch will be occurring in early November, and will be a Falcon Heavy rocket, launching the crew's living module for the next 1.5 years, which will be the NASA MPLM. Now, this is going to have a pre-installed radiation shield, as you see exploding here. It will also have the food, equipment, supplies, and cargo for the mission, totaling to about 14,400 kilograms for our first launch. This is launching to a due east parking orbit, which will be used to assemble all 3 of our spacecraft components over the next period of 2 months. This is in low Earth orbit. It is a 28.5-degree inclination orbit. Essentially, this is the easiest orbit to reach from Cape Canaveral.
Now, in selecting our living module, because of the unprecedented nature of this mission, it was important for us to select the right living module for the job. Now, the Celentano curve is a tool that allows us to estimate the habitable volume for a particular mission duration in space. So we decided, for the 501-day stay in space, to design to the optimal limit. This is 19.4 meters cubed per crew member. So with 2 crew members, this means just under 40 meters cubed is required for the habitable volume. This, plus the food, equipment, supplies, and cargo, means we need 57 meters cubed of our living module. The NASA NPLM, once fully stripped, provides 75 meters cubed, and this excess volume will be dedicated to expanding our experimental capabilities and to really maintaining the mental health of the crew over the course of the mission.
So this is taking us to our second launch, which is going to occur in early December. This is going to be a Falcon 9 rocket launching the crew's command vehicle for this mission. Now, the command vehicle, which we selected as the SpaceX Dragon, serves some key functions for our mission, which are shown on the screen. Now, we compared the SpaceX Dragon to many other options that will be available on the market by 2018 and found it superior for a couple of main reasons. First, SpaceX as a company focuses on fast development and low-cost development. For a 2018 launch, these are absolutely essential to reducing program risk and schedule risk. Second, and maybe most importantly, it has superior re-entry capabilities to any other capsule that will be available. And so this is going to be essential for the dangerous re-entry stage of this trajectory.
At this point in the mission, we've also deployed our Spectral Lab solar panels. These have been custom installed to provide a minimum power generation of 8.6 kilowatts of power. This exceeds our average system usage of 7.8 kilowatts of power and is sufficient to complete our mission. The SpaceX Dragon will now perform the first of 2 rendezvous with the NPLM. This will utilize a common berthing mechanism and 18 Draco reaction thrusters to perform this, and the crew will then set up life support systems and wait for the third and final launch.
So this third launch is going to be another Falcon Heavy, and this is a critical one for the mission. It's launching our booster system, which we have custom designed to be fully fueled and ready to fire to take the crew from low Earth orbit to a trans-Mars injection. So this booster system we designed to be a total mass of 53,000 kilograms, essentially maxing out the launch vehicle capabilities. And that's why the Heavy is essential for this mission. We're relying on the Aerojet Rocketdyne RL-10B2 booster simply for its high specific impulse of 466 seconds. Effectively, we designed this booster system to allow us to bring the most comprehensive and massive spacecraft possible with those technologies. Now, our mass breakdown is shown here. Using the Tsiolkovsky rocket equation, based on the booster that we've designed, we found a mass limit after burn of 26,700 kilograms. Our estimations at this point come out to a total mass of 25,000 kilograms, leaving about a 6.5% margin for growth over the development of the mission. The subsystem division is shown there. So at this point, the extendable nozzle on the RL-10B2 goes into place and fires, applying a delta V of 4.86 kilometers a second. And for the first time, humans are on their way to Mars.
This path to Mars will be a Type 1 interplanetary transfer. This 501-day mission trajectory has been calculated by Patel to be the shortest time of flight and a low-energy burn, occurring once every 15 years. We can see that we will depart January 2018, fly by the Martian planet August 2018, and re-enter Earth atmosphere May 2019 for a total of 501 days in space.
So this is definitely a very exciting time for the crew and everyone on Earth, but it also marks the start of a new and very real danger. Space radiation, as pointed out by the teams before us, comes in the form of galactic cosmic rays, solar particle events. These threaten to severely damage the crew's biological makeup in the short term and the long term. Now, we have never sent humans into this unfiltered space environment for a duration like this. And while it is possible that minimal radiation shielding the crew can survive for the short term, we think it's a very unpredictable risk to take, and thus we've included as many technologies to reduce the exposure as possible. We start by repurposing mass on board as passive shielding. As you can see here, water is one of the best passive shielding materials on this graph. Now, water can be ran, the life support water can be ran through sleeping bags that the crew will spend about 1/3 of their time in. We've estimated with our mass of water that this reduction will be about 10% per crew member for the entire mission of exposure. This is for galactic cosmic ray exposure. We also recommend devoting actual dedicated mass budget to a radiation shield. Now, this is a cylindrical radiation shield surrounding the living module made out of polyethylene. With a 3-centimeter thickness and about 2,900 kilogram weight, we've estimated an exposure reduction of 15% just by itself, on top of the water shielding. Now, this shields the radial direction of the spacecraft, but we also must shield the axis of the spacecraft. To do this, we recommend including a polyethylene, 2 discs, essentially, that the crew will build once they're inside the module. Let's take a look at this animation that's going to sort of clarify this concept. The crew builds these once they're inside, and thus they have a full cylindrical cocoon. Now, these also double as solar particle event protection. In the event of the onboard sensor warning the crew, you can see there the discs will be rebuilt by the crew to thicken passive shielding in the direction of the solar particle event. They can do this in a matter of minutes, and the solar particle event will last for a number of hours, and so protection will be increased for the majority of the event. So this passive shielding scheme we think is going to be very effective, but we've also, in our research, come up with our own active shielding scheme that is a perfect augmentation of this passive shielding. The green cylinders here represent concentric metal plates that will be embedded in the inner and outer surfaces of this cylinder. The cross-section is shown. As these are charged to a high potential difference on the ground, it acts as a capacitor and creates an electric field between the two plates, represented here by the green lines. Now, what happens as a positively charged galactic cosmic ray particle enters this field? Let's take a look here at a theoretical and ideal scenario. This particle enters the field and actually loses velocity, as well as is placed on a curved path by an electromagnetic force due to the potential difference between the plates. Now, some particles may be going too fast and at too high energy to be completely diverted, such as this one, but every single particle will lose velocity as it travels through this field. The plates will be charged on the ground and do not require energy from the ship to sustain. Now, so this passive and active combination, I mean, through superposition, they'll do great effectiveness on their own, but adding them together will actually amplify each other's effectiveness. Our configuration has a breakdown voltage of 660 kilovolts, essentially the ceiling as far as how high we can charge this without discharge across the plates. Through our calculations, we've estimated that a proton traveling at 10% the speed of light, which is a majority of galactic cosmic rays, will lose about 37.5% of its velocity. We have more data showing the range of velocity reduction throughout different types of particles. We think that these combination of technologies is perhaps one of the most effective arrangements at reducing exposure today. And through further research, we can really nail down the exact reduction that this configuration can attain.
Now, as Ben said, the radiation shield will keep the crew safe from exterior harm. However, it's the life support system that will keep the interior of the capsule habitable. The importance of a closed-loop life support system is to reduce the amount of consumables we have to bring with us at the onset of the mission. We've opted to make a completely mechanical closed-loop system, as pictured here. To further understand this, we break it down into 3 subsystems. The first is the air subsystem. This is responsible for maintaining the atmosphere inside the cabin habitable. We will utilize an analyzing interferometer for ambient air to remove any trace gases in the cabin, and an SA9T filter will remove CO2, send it to a methane pyrolysis unit, a Savantier reaction, and finally an electrolysis unit to bring oxygen back to the crew. A byproduct of the air subsystem is water. So water is important for crew hydration as well as food hydration that the crew will consume. And it's also important for filtering out any gray water or products of hygiene activities and to make clean water for the crew to consume. We will utilize a vapor phase catalytic ammonia removal unit, or VPCAR, to do this job. A byproduct of this water subsystem is termed brine, and this will go into one of our 2 waste streams. We have a biological waste stream, which will anaerobically combust any biological waste into its constituent particles or chemicals and recirculate them through the rest of the mechanical loop. And then the non-biological waste stream will compress the waste into thin cylindrical discs, which can then be used to line the interior of the cabin, increasing radiation shielding. You can see that these 3 subsystems work together to close this life support loop and maintain the cabin.
Now, with this system, we do feel we've met the first and most important requirement of the mission, keeping the crew alive and healthy for 501 days. Now, the second priority is maximizing scientific return. This is a great opportunity, an unprecedented mission, and so many space experiments can be done to maximize the return of this mission. We recommend including 3 express racks, as those used on the ISS, to do this. These allow for modular scientific experiments and equipment to be plug and play with the mission. This can be opened up to the scientific community, and spots in this mission can be leased out to increase funding and help with the cost reduction of the mission to Inspiration Mars. This will allow for a diverse research platform for this mission for the 1.5 years that it is in space.
At this point, the crew is reaching the apex of the mission. They're now further from Earth than any human before them, and they will fly by the Martian planet at about 100 kilometers above its surface. During the flyby, the Martian planet will at some point obscure the line of sight between the capsule and the Earth, and the capsule and the Sun. This will cause 2 separate eclipses of both power communication and communications. Power and communications. So power will be handled via our onboard rechargeable batteries, while our communication systems will be blacked out for that brief period of time. The communication systems aboard our craft were modeled after those on the Mars Reconnaissance Orbiter, and they include 1 K-band antenna with 2 supporting X-band antennas for high-fidelity data transmission, and will consume about 350 watts of power on average. On Earth, we will utilize NASA's Deep Space Network, one of the largest antenna arrays available to us, to communicate with the crew throughout the course of the mission.
Now, this is essential, first of all, for mission control information, guidance, and navigation, which will be handled on the ground. But it's also essential for maintaining their mental stability, keeping a connection between the crew and their loved ones back on Earth. This brings us to a very important point to us, is designing the environment for mental stability, essentially, to ease the strain on the crew. Now, through environment design, we think a big priority is lighting. By including an adaptive lighting system consisting of a mesh of LEDs, you can actually replicate Earth patterns that will really help the crew's mental stability. For example, most importantly, we think, is day and night. This will maintain a circadian rhythm of the crew and keep them on a day and night cycle just like they are on the Earth. We also recommend replicating patterns like weather patterns or seasonal things. Just give them a sense of home. You can also do things like give a sense of orientation to the crew in a zero-gravity environment with 1 color corresponding to the ceiling and 1 color corresponding to the ground. Second, noise has been a problem for ISS astronauts. Heavy machinery echoing off the aluminum walls of the ISS has really gotten their nerves and shown it started serious symptoms like anxiety and depression and things such as that. So Silentium is a commercial company that offers an available chip that can be plug and play with equipment and cancel out certain frequencies, essentially negating this negative effect. These are a few of the things we've included in our report for this critical segment of the mission.
In addition to the mental strain, the crew will see high levels of physical strain due to the microgravity and high radiation environment. So we've included a list of medical equipment, which we recommend including on the mission. Two important pieces of equipment to mention are the Advanced Resistive Exercise Device, which will provide resistive exercises to the crew to prevent musculoskeletal atrophy over the course of the mission, as well as the Colbert, which is a passive treadmill, which will provide cardiovascular exercises and maintain the musculoskeletal tissue. It's important to maintain the tissue to make sure that they're safe for the final leg of the journey.
So we're approaching re-entry now, and re-entry, as we've been talking about with other groups, is one of the most dangerous legs. You're going to see high deceleration forces, vibrational forces, and heat generation. Now, the first step, as we're coming in at 14.2 kilometers a second, we're going to use the skip re-entry. And so we think that everything that can be done to reduce the velocity for this unprecedented speed is absolutely necessary. So the first step is to eject the non-essential equipment for the re-entry. This is going to be the booster system and the living module. Now, to slow down our re-entry speed, to lower the risk, we've included a storable booster system in the trunk of the Dragon. This is based on the Aerojet Rocketdyne RS-72 booster with a 340 second specific impulse. We have devoted 2,000 kilograms of booster mass to this system, and this should reduce the velocity of the capsule by about 0.9 kilometers a second down to 13.3. Now, we can't stress enough that this is one of the highest risk sections of the mission, and any excess mass that can be devoted to this system will go a long way to reducing the risk of re-entry. So, as the booster fires and applies this 0.9 kilometers a second delta V, the capsule is reduced down to 13.3 kilometers a second, and is preparing for the direct skip re-entries. Now, we considered aero capture, but we wanted to remove the length and duration of the mission, and so we wanted a direct skip re-entry, as is shown here. Now, the first skip has a peak G-force of about 4.5 Gs by our calculations, and following the skip, there will be a serious pilot input to keep the capsule in the upper atmosphere and stop it from shooting back out into space. The peak G-forces throughout the entire re-entry process will be about 5.2 Gs, which our physical health group has deemed acceptable. We're approaching our final ballistic re-entry, which will be about 3.5 Gs peak, I believe. And at this point, the Dragon's parachutes will deploy in the upper atmosphere, and the Dragon will head to a relatively gentle landing in the Earth's oceans. So I'm sure you're interested in our cost estimations, as there are some novel systems here. We've estimated a system cost of $1.7 billion, which you can see represented by the pie chart broken down by system. Now, our cost philosophy, we'll give you an example with the life support system, which is a very obviously costly one by our pie chart. We started with the Advanced Mission Cost Model, a tool that gave us a life support estimate from the ground up, essentially a system from scratch. Then we broke our life support system down into different subsystems, air and water system, and then looked at the technologies that we had selected for those systems, assigning technological readiness levels per component. Then, aggregately, we adjusted the cost of each segment up and down depending on how ready the technology is today and how much development must be done to make it ready for a 2018 launch. Adding the cost back up, we feel we got a much more accurate estimate of $1 billion about for the life support system. Now, this was applied to every other system to get a more customized cost analysis for the mission. We also prioritized for commercially available, off-the-shelf parts. And finally, we wanted to use equipment that had already been developed. That, for example, the communication system was used on the MRO. This will be stable and reduce the development cost for this mission. Operational cost is $1 billion, which is approximating things such as program implementation and staffing costs, things such as that.
So at the onset of this mission, Inspiration Mars requested a comprehensive mission design, meaning launch to re-entry. It also requested a 2018 launch date. So while we've striven to hit these goals, we've also striven to make it low cost, safe, and simple. While not all of our subsystems can currently hit that, we feel that overall our mission design does hit that, and with the correct partnering of certain companies, we feel could be ready for a 2018 launch.
So with this mission design, we feel we have answered the competition prompt given by Inspiration Mars. But most importantly, we hope that our design and any of the ideas that we've shown you today can actually contribute to the efforts of Inspiration Mars in making this mission possible. Our team and every other team I know really wants to contribute to the Martian effort, and that Inspiration Mars and Mars Society is striving for. And we're very excited to see the entry of private industry into the leadership role in space. So with that, I'd like to invite some of our section leads up to the stage, and we can answer any specific questions that you have. Please.
Similar to the one on the first group I asked, so you use some really good heritage stuff like MPLM
Right.
and Dragon, and these environments are quite a bit different. Like MPLM is not made to launch vertically, right, or do docking loads.
Sure.
So did you guys, and the entry's a lot different than Leo, so how did you guys accommodate that, let's say, in your overall mass estimate? Did you take that into consideration, what modifications you would have to make to the heritage systems?
Sure. The MPLM, I think, is definitely a significant one. And really, we mostly estimated that through cost allocation.
Okay.
So adding our margins to the cost, that we thought would account for the development cost. Essentially, that's structural concern, right? When you're launching vertically rather than inside the space shuttle.
Right.
So that is going to be some of the development cost that comes about. We don't think that's a showstopper, really. And so we just figured it's going to cost more money, and you're going to have to spend that money in development. Yeah.
Yeah, I noticed that you allocated 3% in your budget for this radiation shielding system. Can you cite any heritage for the active part of that?
Yeah, we actually think that this is a pretty novel concept that our radiation team has developed. So we want to.
I'm sorry, I'm not familiar with the term heritage.
Any past demonstration that this capacitive method would in fact do what you say it does?
Okay, so the basis of the shield is actually fairly electrostatic interactions between particles and an electrostatic field. But as far as like past stuff is concerned, I know the National Lab in Los Alamos is currently working on high voltage situations like this and charging to high voltage situations. So a mixture of the research that they're doing there plus the basic fundamental physical properties of the nucleus versus an electrostatic field would sort of a culmination, I guess, work in this case.
Right. Just quick follow on, one of the issues with radiation is that interaction with the shielding material and the ionizing particle produces secondaries.
Yes.
And did you consider that?
Yeah, the high-density polyethylene has low secondary shower rates, and that's one of the primary reasons it was actually used as a shielding method. We're active with that.
Right, and our active shielding, I think, produces Bremsstrahlung radiation. I think that's how it's pronounced. And so those are secondary photons, I think, that are given off as the energies interacted with. And passive shielding is effective at stopping those particles.
On your active shield, you had a 660 kilovolt potential. How is that going to stop a gigavolt cosmic ray particle?
So the high energy events in particular, like one case I was considering was 0.5C iron nuclei. Those wouldn't be stopped, but they would have velocity reduction, which would allow more time potentially for the passive shield. And it would, each particle has a certain mean free length in which it interacts with any particle that is in its way, in our case passive shielding, and it would increase the basic amount of time that they would pass through our passive, which would theoretically make our passive shielding more effective. So each particle would experience velocity reduction, basically, and that would be without any additional weight too, which would be handy.
Yeah, the damage would essentially be lessened, although it still would improve definitely. Yeah.
Especially the higher energy events like that.
Did you look at what defines the length or number of launch windows you have for that third launch?
Yeah, we did actually. Carlos mentioned that.
Can you reword your question, please?
What's the length of the window, or did you look at how many launch opportunities you have for that third launch?
Third launch specifically?
The third launch you have that launches the stage. You have 3 launches, right?
Right.
Your last launch launches the stage.
Yes.
What constrains the windows on that launch window?
Well, basically it's a tight window, and so we propose that the launch take place on the 1st of January with an assumption of 3 days to catch up to the rest of the spacecraft, such that we can perform the booster burn on the 5th of January 2018 in order to meet the time constraint proposed by Telsec.
Yeah, cryogenic boil-off really is the limit, of course, with this launch window. It's making it so tight, and that is a risk of the mission, but we balance between how much boil-off would happen and when we think as much launch window as we can afford for this third launch.
Other questions?
You seem to have a relatively complex life support system in the sense that you were trying to recover as much as you possibly could. Given you had almost 3 tons of polyethylene shielding, do you think you could have balanced perhaps putting more water into the vehicle and cut down the complexity?
Yeah, I mean, so that would essentially, the water doubles as radiation shielding. I think that's why it's effective. We could do that, but it really is not as effective of a passive shield, and the polyethylene does serve a dual role as the dielectric in this capacitor arrangement. So the greater the distance between the 2 plates, and I believe this is right, what Stephen's told me, the greater the distance, the greater the breakdown voltage you can charge these plates up to. So essentially, the more polyethylene we use, the more effective the active shield is. So it is a balancing act there. We had the passive shield even with greater mass before, but we figured 2,900 was a good balance with all the elements of the mission.
And by having a more complex life support system like we are, we're facilitating a next step of having a more complex mission in the future. We're going to be striving to have a closed-loop life support system, so the closer we get to that at this point, the easier it will be to take the next exploratory step.
Quick question. Have you considered what happens if you don't make the 2018 launch window and slip to 2020?
Yeah, that's a risk, and essentially it would increase the length of the mission, right? The trajectory is not as short as it is. And so that would take some redesign to increase the mass of supplies we bring to the mission. And we have looked at that. I think the new trajectory is 570 days, if I'm correct. But it essentially increases the amount of mass we're going to have to bring. And we have looked at that. We think we have room on the first launch, especially for many more supplies at a 14,000 kilogram first launch. So this would not be a disaster. It is a risk, but it wouldn't be a disaster.
What was your total gross liftoff mass? I couldn't tell.
Oh, total system mass? All 3 components?
Yeah.
I think it was 77,000 kilograms. It's about there. Yeah, about 77,000 kilograms.
Did you, so conceivably you could do that with 2 SLS launches. Did you consider the SLS then?
Yeah, of course.
Given that it would reduce the launch and maybe reduce the docking complexity?
Essentially, we felt the program risk, schedule risk of the SLS. I mean, I don't think the SLS is scheduled to launch first unmanned until 2017. That's correct. So for a 2018 launch, it just didn't seem like a realistic option. In the future, it's probably going to be the superior option, but there's constraints on this competition.
Okay. So published launch dates, that's what you used
Right.
to assume. Okay, okay.
Why not 2,000 ago you had a 77 tons to work?
So we would have to launch the MPLM and the Dragon in the same payload, which would kind of complicate things. And we think that the cost, the launch costs of the Falcon launch vehicles, they're a small percentage of the cost of the mission. So by reducing complexity through the launch configuration into a single Dragon on Falcon 9 and an MPLM and the payload of Falcon Heavy, we actually think this is less complex mission. Okay, thank you.
Okay, thank you very much.